Hi everybody, we're going to go through the multiple regression script from Biostats the other day, since we kind of went through it pretty quick, just to make sure you all have a grasp on it. So for this script, and with any script that you are working with in Biostats, the first thing you must do is set your working directory. And if that hasn't already been drilled into your head, set your working directory before you try running the script. Okay, so there are two ways that you can do this. You can either go into your main computer folder and navigate to the proper folder that contains the data that you want to be working with. Right click on the header, copy the address as text, and then paste it into your source as so. And then change all of these backslashes to forward slashes. Or, and make sure it's not cap lock, sorry. Or you can go into the session tab and set your working directory from there, doing what I'm doing here on the screen. And just click on the whatever folder that you need. So this is my working directory. This is not going to be the same as yours, so don't freak out if you type in what I have here and it doesn't work. All right. So in order to run this script, we also need 3 packages. Now, if you weren't able to download these packages, you can download them as so by going to the Packages tab in your viewer console and click Install, and then type whatever package that you need. Click on it and then install. I, however, already have all of these, so I can just run this real quick. All right, so we have everything that we need to get started. So we're going to work with the Perullo data set for this section of the script, and it contained a number of variables, the ones of interest for us, C3 and C4 plants, JJ map, which was seasonal precipitation, MAP, which was mean annual precipitation, MAT, which was mean annual temperature, DJF map for total precipitation falling in winter, and then longitude and latitude. So we're going to tell R to read the CSV. This is where our data is that we want to analyze. Then we can just take a peek at the data, make sure everything came over nicely, and start looking over the actual data set to get a feel for what we're working with. So we need to get a sense of the variables, especially for multiple regression, because the variables play a role in going through the assumption testing and actually will be a large part of, well, they are our models. So you can't just put in a whole bunch of variables, you need to learn about them first. So let's start with our response variable, which is going to be the C3 plants. So we're going to first change the margins of our plot screen, just so we can view the plots side by side. So looking at the box plot and histogram, we want to look for kind of at their normality of the data. So right off the bat, we can tell that this is a non-normal distribution. You have a right-tailed skew here, where most of your data is clustered towards the left end of the histogram. And that's further substantiated by the box plot, where you see this large tail occurring, extending into the high region of the data. So that's something that we should keep in mind, that we have a non-normal distribution with this C3. So let's look at the other variables. All right, well, we have some outliers here, but other than that, it seems like MAP has a pretty normal distribution. And we're not going to make any changes yet. We just want to look at our data. All right, so here, I mean, latitude looks fine, nothing that's concerning. This one looks like another distribution that might have somewhat of a right-tailed skew, but nothing horrible. JJ map looks fine. I mean, it's kind of boxy and funny looking, but not in a non-normal way. Here you definitely have a right tail skew. Again, you can see the extension of the maximal end whisker. And let's look at longitude. Longitude looks fine. I mean, you can't get much better for a normal distribution with this box plot. Histogram looks a little funny, but box plot looks fine. All right, so with multiple regression, it's different from your t-test, from the ANOVA test, in that the normality assumption is based on your y variable. You're testing under the assumption that the residuals are normally just distributed. So you're really focused, as far as normal distribution, you're really focused on your y variable or your response. It's okay if the variables that are going to serve as predictors are non-normal, because the assumption is that you have normal distribution of your y variables or your y values across each x value. So again, we really want to make sure that when it comes to normality, it's occurring in our y variable. Now, our y variable, or our response, as said before, is C3, the C3 plants. So if we go back up to the box plot for C3, remember we said, bad distribution, you have a non-normal distribution here. So that's of concern because this is our response. So we can further substantiate that's non-normal by testing with the Shapiro-Wilk normality test. Now with this normality test, when you get a p-value that is less than 0.05, it means you have a non-normal distribution. So here we have less than 0.05. So this verifies my statement that the distribution of C3, the response variable, is not normal. So we need to change that in order to meet this assumption. And there's different avenues of change. We could do a non-parametric alternative, or easier, we could just do a transformation. Now, seeing that we have a right-tailed distribution here, the first thing that comes to my mind as far as transformation is a square root transformation. As such, works pretty darn well with that kind of distribution. So again, we're going to reset our margins just so everything is on the same playing field. And we'll run a box plot of the normal variable and then a box plot with it transformed, as you can see here. So when we run the square root transformation on the C3 variable, we produce a pretty normal distribution. That looks great. But we can't put our eggs all in one basket. We need to check the other transformation as well, which is log. Log could also work in this scenario. So let's give that a test. And that is just an epic failure. It's basically this original plot just flipped on the horizontal. So let's go with the square root transformation. So we're going to tell R that we're going to make a new attribute called C3 square root. And that is formed by taking the square root of this C3 variable found in the Perulo dataset. So let's run that line. So now we've created a new variable right here, a new value. And we can check that in our global environment. We're going to make another one because we need to make a new data set. Well, it's not that we want to make a new data set. We need to combine our new attribute into our original data set, which we're doing with the cbind function. So we're taking the C3 square root value that we just created, and we're binding it to the original Perula data set, forming a new attribute that we're calling Perula trans. So we're going to run that, and you can double check yourself by making sure it exists by checking your global environment. And we see here that we now have our new data set that we're going to work with because this contains the proper response variable. 73 observations and 9 variables. All right, so we can check off one assumption. So we checked the normality assumption and we dealt with it. The next assumption that we need to deal with deals with multicollinearity. So we need to check and make sure that there is no collinearity among or between any of the variables, and that there's no relationships occurring between them. So we can do this visually by running the pairs function to make a scatter plot matrix or SPLOM of all the variables. So we're going to do that here. I'm going to zoom out so we can get a better picture. So looking at this, oh, right, okay. So real quick, I'm just going to run this real quick, get rid of the C3 variable, now run this. Sorry, I got ahead of myself a little bit. So I took out, by running that C3 null, I took out the original C3, so that's replaced with the C3 square root. So along this horizontal line, C3 square root is serving as the response variable. If you assess it vertically, C3 square root is your predictor variable, which you don't want. You want C3 as your response. So we're going to look for relationships in this direction. So right off the bat, I see a possible positive correlation or positive linear relationship here between C3 square root and latitude. You might have a negative relationship going on here between C3 square root and mat. And I mean, there's probably a negative correlation here, which is kind of disregarded for us. But what we really want to look for is any relationships occurring in here between your predictor variables. So first thing that jumps out is that you have possible relationships right here occurring between JJA map and DJF map, both of which look to be negative correlations. There's also possible positive correlations between DJF map and longitude. You see nice correlation lines here, or regression lines, I should say, sorry. There also might be a relationship here. There might be a relationship here. There could be one here between latitude and mat. So these are all things that we need to keep in mind. There's definitely area of possible collinearity. So we see that visually, but we actually need the numbers to make a better comparison. So you can run this. It's not going to work on this computer. I don't have the most recent version of RStudio, which you kind of need one of the newest models in order to run this package. It's called Deducer. It's a great package if it works. It's basically an intuitive cross-platform graphical data analysis system, and it uses basically these menus and dialogues to guide the user through data manipulation and analysis, and can make Excel-like spreadsheets for cool data frame visualization, and has advanced editing. It's a neat program, and it has really great ability to import data and to view your data in different variables or building plots. But for most of us, it's not going to work. And that's okay. It's not a lose-all situation, because it basically gives us the same information that we can gain from the scatter plot matrix, just not as pretty and not as awesome. And it's not a deducer, but that's okay. So we're going to skip over that. This I jumped ahead of myself and already did. This was where I took out the C3 variable, and that's why it doesn't show up in the scatter plot matrix. All right, so in order to, so we saw the visually where there might be collinearity, but now we need to actually test if those possible collinear relationships, if they are actually something that we need to worry about. And we're going to do that by testing the variance inflation factor, or VIF. So first you need to build a full model, or a linear model that contains your response variable and all of the predictors that you're interested in, or all of the predictor variables in your data set. So that's this line here. We're making a new attribute called model full, and that's the linear model of the C3 square root as the response, or our Y value variable, with all of these predictors. So then we're going to test the variance inflation factors of that model. Now, our results that are produced all look fine, and that's because none of them are at 10. If you have a variance inflation factor of 10, that means it has a high degree of multicollinearity, and that you need to remove one of those factors that it's kind of relating with. All of our variables, again, are below 10, so we're okay. There is evidence of collinearity, but nothing influential enough that bears needing removal. So we can move on. Basically, we've met that assumption. We're okay. So we're gonna, just for simplicity, we're gonna make our first model looking at just latitude and longitude. This is not typically what you do for regression. You look at all of the factors together, but again, just for simplicity, let's start by building a really simple model. It's like eating an elephant. In order to eat an elephant, you take one bite at a time, or a whale, whatever you want to eat. Okay, so first we're just going to reset our viewing screen margins, and we're just going to run 2 plots with smoother lines to see if there's a possible linear relationship or how, like, what direction that regression might be moving in. So here we see a nice spray of the points. We don't see any wedge shape, which is good. So again, that's doesn't mean, it means that there's no non-normality here. And you see that there's a possible positive correlation between latitude and C3 square root. So that looks fine. All right, so we're going to build a model, a linear model, that's built with C3 square root as the response and your latitude and longitude as your predictors. So we're going to code for that, and then we can run the model. So if you just run model lat long, you get a kind of crappy output. You don't get a lot of information. So we're going to look at the summary, and that gives us a much better idea of what we're working with here. So let's see what's in our output to interpret. All right, well, looking off the bat, we can determine our adjusted R-squared value. Now, if you remember, we use the adjusted R-squared to tell what percent variance this model actually accounts for, or how much of the variance these factors are accounting for in the total model. So with this adjusted R-squared, we can see that the model we have built accounts for roughly 46% of the variation in the model. And again, we use the adjusted R-squared to determine this, not the multiple R-squared, the adjusted R-squared. We can also look at the p-value to determine whether it's significant or not. So we have a value here that's less than 0.05, meaning that our p-value is significant. So we have our model has a significant relationship, or that these two variables significantly influence C3 square root. So looking up here, I want you to disregard the intercept. Yes, the intercept tells you where on the plot your line's actually falling or starting, but intercept is actually a nuisance variable. For what we're trying to determine right now, it doesn't provide any importance. If you were actually constructing the y equals ax plus b or y equals a plus bx formula, you would need your intercept value. But right now, it's a nuisance. We don't need it. So let's look at just the latitude and longitude. So we can determine that latitude is more influential than longitude, or that latitude is displaying a lot of the variation, longitude is not. We can determine that because of the significant p-value in your latitude. We can also determine the actual movement of the correlation, or this regression line. So latitude has a positive relationship with C3 square root, whereas longitude, in the presence of latitude, has a negative correlation. And I think that's pretty much what you can get from that. So next thing we're doing is running residual plots, and this is part of running the diagnostic test afterwards. So again, we're going to reset our margins, and we're going to test residuals versus the fitted values of the model that we built. And what we're looking for is a spray pattern of your points. So here is a great example of what I mean by spray pattern. You have your points nicely distributed evenly across the surface of this plot. If you had most of your points clustered over here, or a big cluster here, or a cluster here, we would say it was wedge shaped, and that's not normal. That's not normal distribution for a residual plot, and that would be something of concern for us. So what we're seeing is a normal spray pattern, meaning we have normality in the distribution of our residuals, which also checks off one of the assumptions, so that's great. We're happy we can move on. So this isn't the only residual diagnostic test you can run. By just putting the model in the plot function, you can bring up these 4 default plots that kind of run in the background and then are produced by R. It kind of spits it out at you. The 2 that I think are most important are in the normal QQ and your residual versus leverage. So normal QQ, you're seeing the movement of your points along or in comparison to this linear line. And you can see that most of your points fall along the line, which is good. You have a couple worrisome points, 57, 66, and 25, that kind of fall a great deal away from the line, and R is kind of flagging those as they might be worrisome. But we can tell from the residual versus leverage that they are not. That even though they are a little bit off of that regression line, they're not anything that would be influential to the model or anything that should be of concern to us. And we can determine that again from the residual versus leverage plot because they're within the Cook's distance. So when you have a Cook's distance plot, usually you'll see 2 dotted lines up here and down here, 0.5 and 1. If you have a point that falls outside of those lines, so if you have a point that falls is greater than that 0.5 line or the 1 line, that's an influential point, and that's something that you need to deal with in your model. But here we can see that all of these points are within the boundaries of those lines. Again, here's some of the points that were highlighted to us in the normal QQ plot, but again, we can see that, yes, even though they had some concern up here, it's nothing that is going to be influencing the model to a degree that needs to be dealt with. So if you also wanted to look at the Cook's distance, the actual numbers, you could, but most of us have lives and don't want to sit here and go through all of these numbers, so it's easier to just see on the residual versus leverage plot. But if you wanted to, if you saw, say, one of these points, and you wanted to call out what that maximum point was, you can call for it with the Cook's distance. So you can call out what the maximum Cook's distance is, and then to see if there's one that you should be worried about. And then also code for which ones R thinks you should be worried about, and you can look at them in your data or look at them on here and see if they're influential or worrisome points. Okay, so let's run a summary of the model that we've built using latitude and longitude. We get an output that I've described previously, but the one thing that we don't get in the output is the confidence interval. So this is the 95% confidence interval for the model using latitude and longitude. And you can determine significance in the confidence interval if it based on whether or not it contains 0. So latitude, the confidence interval does not contain 0, meaning it is significant. Longitude does contain a 0 in its confidence interval, meaning that longitude could equal 0, which causes us to go with the assumption that longitude is not significant, which is also shown up here. All right, so we can run some partial regression plots or AV plots just to see some of the partial regression slopes. So you can see this is for longitude, this is for latitude, very similar to the plots that we ran previously when we were just kind of getting a sense of whether there was linear or non-linearity with them. And if we wanted to specify or call out a single variable, we could do so by coding for it with variable equals whatever the variable name was. So we're just seeing basically double of the longitude in the presence of or in relation to the other variables. So we'll come back to this little area here in a moment. So, as I said before, the model that we built with latitude and longitude is not something that you typically do for multiple regression. The whole purpose of multiple regression is that you have 2 or more predictor variables, and you want to see which of those variables kind of build the best model or is most influential to the response variable that you're testing. So most of the times you can either form hypotheses in the beginning. A lot of times you'll end up just clumping all the predictors together that you found to be of interest from your scatter plot matrix, and you will test those. So here we're testing, there's 4 models that we're building based on the hypotheses that we want to test. So we're going to test the C3 square root in regards to latitude, longitude, latitude and longitude, and map and latitude. So those are the 4 plots. So we built them and they're now in our global environment. So let's pull up the summaries for each of them. Now with each summary, I want to draw your attention to the adjusted R-squared value. When you're choosing, what we're doing right now is choosing the best model of the 4 that we are hypothesizing about. And in order to do that, again, draw your attention to the adjusted R-squared. The best model will have the highest adjusted R-squared. So let's scroll up. Oh, you turd nugget. Okay, so let's scroll up to the beginning. All right, so first one we want to test is the model with just latitude. So that gives us an adjusted R-squared value of 0.46, meaning 46% of the variation it accounts for. Model long is just horrible. We get a negative R-squared value, so we definitely don't want to use that. The longitude and latitude, we get an adjusted R-squared value of 0.46, so it's a little bit better than your latitude. So if you had to choose between just those 3, you would go with the latitude and longitude because it has the higher adjusted R-squared. But we have another model. Remember, we have 4. So the model map latitude gives us an adjusted R-squared value of 0.4868. So of the 4, this model, your model map lat, has the highest adjusted R-squared value, meaning it is, according to adjusted R-squared values, it is the best model. And remember, the higher the adjusted R-squared, the better the model. We can also do model testing with AIC values. So looking at this, with AIC value, you want the lowest AIC value for the best model. So looking at our results, the lowest AIC occurs with the map latitude, substantiating our notion that that was the best model based on the R-squared value. So there's another way, we didn't go over in class, but there's another way that you can do model selection, and this is through stepwise analysis. Stepwise analysis takes the all of the factors that you are coding for, so you tell what predictor variables you want to include, and it separately takes out each one from the model and it sees what the change to the AIC is. So the end result is whatever one gives you the lowest AIC is the best model. So I'll run that for you just so you can get an idea with just the longitude and latitude. So what you see here is the model when it contains longitude and latitude. Its AIC, or its starting AIC, is negative 224.45. When the model does its stepwise analysis, so it's taking out longitude and just testing latitude, that transition, that by taking away longitude, you actually increase your AIC, which is bad. So this model here, C3 square root tested against longitude and latitude, having those as both predictors, is a better model than just having latitude. So that's, again, another way of analysis, but we didn't use it in class, but just in case you were interested. So again, we determined that our best model was the MAP-LAT, so we're going to run a summary of it. And we get a significant p-value. So there is a significant regression relationship between map and latitude and your C3 square root. Or you can say that there's a significant relationship between C3 square root, map, and latitude in the presence of map and latitude. This model itself accounts for roughly 49% of the variation of the total model based on its adjusted R-squared value. Now looking up here again, disregarding your intercept because it's a nuisance variable, we can see that both latitude and your map variables are significant to the model. They both have significant p-values, and they both have a positive correlation. So latitude and map have a significant positive correlation with C3 square root in the presence of each other. And so just to double check all of our work, we can reset our margins, and we can just plot the model that we've run. We can do the residual testing. Again, we have no points that fall outside of the Cook's distance that are worrisome. Most of the lines follow this, most of the points follow the regression line, which is good. Let's run the Shapiro-Wilk test for normality. We get a p-value that's greater than 0.05, meaning we do have a normal distribution, which is great. And this is for the residual, so our residuals follow a normal distribution. Running an AV plot, we see some nice linear relationships here. We don't see that somewhat what was going to a straight line with the longitude, which was kind of a little worrisome, but what we see here are definite linear relationships. And then let's run the variance inflation factors again, just to make sure that there's no collinearity, and we get values that are well under 10, so nothing to be concerned about. So that means all is well and good for us. There was one thing that I skipped back up here. Here we go. So if we wanted to do an ANOVA to do an F-test, just to do some null hypothesis testing, this is for, what model is this for? Okay, so this is testing an ANOVA against the latitude model and longitude model. So this is showing that basically the influence of longitude on the model is not significant because it does not, when you take out, when you add longitude back into the model, it does not have significance. So that's kind of just showing how to interpret it using the ANOVA. But yeah, so that's multiple regression. Again, the important things to do is to run through, check your assumptions, and then do analyses to analyze what the best model is based on your predictors or what your hypotheses are, and then double check that your model fits the assumptions and do whatever necessary changes you need to make to fit those assumptions. And that just about wraps it up with a pretty pink bow. So yeah, if you have any questions when you're working on your group stuff, remember you can email me or visit me during office hours. I like company. And I think that's all for now. So you can give yourself a pat on the back. You completed multiple regression, and you can now go to sleep peacefully.